Good morning, class. Glad to meet you. Okay, my name is Peng Weijie. I'm so excited to be your teacher this time. My QQ number is 344-75528, and this is my email address.
Okay, teacher.
Okay. This is our textbook. It includes 14 units. Our class will cover several units of these, such as strings, screw thread, belt drivers, chain drivers, gear drivers, shafts, and and bearings. Okay, we will learn each unit for 4 to 8 hours. Oh, sorry, I have a cold. Okay. So the exam will be based on what you have learned, and the exam will be an open book test. It won't be too hard if you are well prepared. And this is the test question of last year. You can refer to it. It included choice questions, okay, and true or false questions, and calculation and analysis questions. We also have 4 hours experiments, which will be planned to be completed in 2 weeks. Okay, maybe in 16 and 70th week. And in the 14th and 15th week, we have a course design. Okay, and our course, machine design, involves many decision making, including engineering ones and non-engineering ones. The engineering ones include loading and materials, strengths, and so on. Okay, machine design involves almost all the disciplines of mechanical engineering. First, you should familiar with engineering materials and their properties, materials processing, heat treatment, and the manufacturing process. Second, you should know knowledge of turbulent fluid mechanicals, heat transfer, and then you should master some draw tools. For example, you should master the CAD. So you need to have some knowledge of preparation course. The preparation courses including engineering materials, theoretical mechanicals of materials, heat transfer theory, and engineering drawing and CAD. Okay, the purpose of our course include master fundamental design principles of various machine elements and basic knowledge methods and procedures, and gain the competence in applying them into practical design. Okay, machine element design is the design of mechanical elements or components consisting of capacity calculation and structure design. The considerations of machine element design are similar to those of machine design, with more concerns on safety, manufacturability, cost, codes, and standards. And the okay, and the design procedure include selecting a suitable type of machine element and estimating the size of machine element and evaluating the machine element's performance against the requirements, and then modifying the design and the dimensions until the performance is near to which the optimum is considered most important. Okay, in the design process, potential failures are prevented by proper material selection, reasonable assumption and simplification of operating loads, correct shape and dimension determination through accurate strength, rigidity, and other relevant analysis. Common failure modes in machine elements include deformation, yielding, fracture, fatigue, pitting, and spalling, well, curling, and sear, corrosion, creep, buckling, and so on. This is the picture of deformation. A deformation includes elastic and plastic deformation. When stresses generated in an element exceed yield stress, plastic deformation or yielding occurs. Both elastic and plastic deformation may cause malfunctioning of machine elements. For example, the deformation of a shaft will prevent gear smashing properly. And this is a picture of fracture. Fracture may occur in both brittle and ductile material due to either static or fluctuating loads. Ductile fracture occurs when plastic deformation reaches the extreme in ductile materials, leaving a dull, fibrous rupture surface, and brittle fracture happens when elastic deformation achieves the extreme in brittle materials, leaving a granular multi-phase fracture surface. The picture on the left represents the microstructure of ductile fracture, and the picture on the right represents the microstructure of brittle fracture. Okay, this is a picture of vertical. Vertical fracture is a sudden failure It takes place due to the initiation and propagation of a microcrack under fluctuating loads over a period of time. The loads causing fatigue are usually far below the static failure level. In order to better learn the knowledge of machine design, okay, now let's review the key points of engineering materials and their properties. Okay. For engineering materials, our object is to master the classification of different ferrous metals and be familiar with the lengths of ferrous metals. Okay. Engineering materials include metals, polymers, and ceramics. Metals can be classified as ferrous and non-ferrous. Ferrous such as irons, carbon steel, alloy steel, stainless steel, and so on. And non-ferrous include aluminum, copper, magnesium, nickel, titanium, and so on. In our course, we focus on ferrous metals because most of the mechanical elements are made of ferrous metals, such as hammer, shaft, and screw. A ferrous is divided into two classes, steel and cast iron. Okay. This is the iron carbon phase diagram. Those with a carbon content greater than 2.11% are cast iron, and those with less than 2.11% carbon are steel and cast iron. In terms of carbon content, the carbon steel is further divided into three classes. Low carbon steel, medium carbon steel, and high carbon steel. Okay. Low carbon steel are used for such operations as bearing, cold bending, welding, threading, and so on. They are low responsive to normal heat treatment, but for case hardening. Products such as screw layers, nuts, bolts, washers, wire fences, light and heavy structure members, machine parts, forged parts can be made from low carbon steel. It is also used for template and automobile body sheet. It is available in form of sheets, squares, rounds, plates, and wire. And the carbon content of low carbon steel is less than 0.3%. And for medium carbon steel, they are less ductile but harder and have greater tensile stress than low carbon steels. They also have better machining qualities and are more responsive to heat treatment. Medium carbon steels are used for making shafts, connecting rods, motors, rear axles, gears, turbines, bucket wheels, steering arms, and other machine parts requiring medium stress and wear-resisting surface. The carbon content of medium carbon steel is less than 0.3% and less than 0.6%. And high carbon steel used for making hand tools such as this. And the carbon content of high carbon steel is from 0.6% to 1.7%. And in terms of material structure, the carbon steel can be classified as Eutectoid steel, hypo-eutectoid steel, and hyper-eutectoid steel. At room temperature, the microstructure of eutectoid steel is perlite, and the microstructure of hypo-eutectoid steel is perlite and ferrite. For hyper-eutectoid steel, the microstructure is perlite and cementite. Okay, this is the structure of ferrite. Ferrite is soft and ductile, has body-centered cubic structure, and the interatomic space are small and pronouncedly oblate and cannot readily accommodate even a small carbon atom. Therefore, solubility of carbon in ferrite is very low, of the order of 0.006% at room temperature, and the maximum carbon content in ferrite is 0.0218% at 723 degrees Celsius. In addition to carbon, a certain amount of silicon, manganese, and phosphorus may be found in ferrite. And the picture on the right is a metallographic photograph of ferrite from the iron carbon phase diagram. We can see that this is the error of single ferrite, and the solution of carbon is small, like in this temperature is 0.0218%. Okay, and it's the structure of oxalate. It is a face-centered modification of iron. It is the stable form of pure iron at temperatures between 910 degrees Celsius and 1400 degrees Celsius. And at its stable temperature, oxalate is soft and ductile, and consequently, is well suited for manufacturing process. For example, forging. And the face-centered cubic structure of iron has large interatomic spacing than in ferrite. The interatomic spacing. Even so, in FCC structure, the interstices are fairly large enough to accommodate carbon atoms, and lattice strands are produced. As a result, not all the interstitial sites can be filled at any one time. The maximum solubility is only 2% of carbon at 1130 degrees Celsius. Next is from the phase diagram. This point is the solubility of carbon in oxalate is about 2% or 2.11%. Okay, for that iron, about 1400 degrees Celsius, oxalate is no longer the most stable form of iron, and the crystal structure changed back to a body-centered cubic phase called delta iron. The solubility of carbon in delta ferrite is small, but it is appreciably larger than in alpha ferrite because of higher temperature. The maximum solubility of carbon in delta iron is 0.1% at this temperature. Okay, let's see the phase diagram. Oh, there is delta iron, and there is alpha ferrite. Okay. The cementite. In iron carbon alloys, carbon is excess. The solubility limit must form a second phase, which is called iron carbide or cementite. Iron carbide has the chemical composition of this, and this does not mean that iron carbide form molecules of this, but simply that the crystal lattice contains iron and carbon atoms in a 3:1 ratio, and the compound cementite has an orthorhombic cell with 12 iron atoms and 4 carbon atoms per cell, and thus has a carbon content of 6.67%. The white part is cementite. As compared to austenite and ferrite, cementite, being an intermechanical compound, is very hard and brittle. The presence of iron carbide with ferrite in steel greatly increases the strength of steel. Okay. This is the iron carbon phase diagram, and the solidification of liquid iron and carbon melt begin along the liquidors denoted in the figure by A, B, C, D. Above the liquidors, the alloy is in a liquid state and is a homogeneous system. Along the liquidors A, B, the crystals of the solid solution of carbon in delta iron are separated from the liquid. The region A, H, N, there is single phase region of delta iron, and the region N, G, E, S, G, there is single phase region of austenite, and the region GPQ, there is single phase region of ferrite, and then the region GSP, there is the two-phase region of ferrite and austenite, and the region SECFK, there is the two-phase region of austenite and cementite. Okay. Crystals of austenite are separated from the liquid along the line B, C, with the composition ranging from 0.18% to 2.11%. The complete solidification of these alloys proceeds along the solid line H, J, E. Alloys containing 0.18% to 2.11% carbon become solid along the solidors H, J, E. Those with 2.11% to 4.3% carbon are completely solidified on line E, C. The solidification of the last portion of the liquid phase, enriched in carbon to 4.3%, takes along this line. All this liquid is completely solidified at this temperature. And is the eutectic reaction temperature. At the same time, crystals of oxide containing 2.11% carbon and cementite containing 6.67% carbon get separated from it. The solidification of alloys containing 4.3% to 6.67% carbon begins along line CD, with the separation of primary cementite from the melt. And at the lower temperature, the eutectoid reaction, formation of two solids from a single solid occurs at a temperature of this temperature, 727 degrees Celsius. This is called the eutectoid temperature, and this line is eutectoid reaction line. And the composition at which this reaction occurs is called the eutectoid composition. Okay, this is the eutectoid reaction line. And the reaction may be shown as follows: austenite reaction transfer to ferrite and cementite. Okay. In the reaction, the simultaneous formation of ferrite and cementite from austenite results at a temperature of 727 degrees Celsius and compositions of 0.08% carbon. Since the ferrite and cementite are formed simultaneously, they are initially mixed. The mixture is laminar. It is composed of alternate layers of ferrite and cementite. This microstructure is called perlite, which is very important in iron and steel because it can be formed in almost all steels by means of suitable heat treatment. Okay, this is for carbon steel. Okay, and this is the composition of eutectoid steel. The alloy containing 0.8% of carbon is called the eutectoid steel. And upon cooling the eutectoid steel below the temperature, all of the austenite oxalate is transformed into perlite. Alloys with less than 0.8% carbon are called Eutectoid steel, and those with higher composition are called Eutectoid steel. Okay. Oh, for cast iron, the shape of graphite present in cast irons would greatly affect its strength. When it the ferrous alloy which have carbon content of more than 2% are called cast iron, and from the iron carbon equilibrium diagram, it can be observed that irons have essentially cementite and ferrite. Because of the large percentage of carbon, the amount of cementite is high, resulting in very high hardness and greatly qualities for cast iron. In the presence of graphitizing elements such as nickel and silicon, iron carbide, the cementite, decomposes as follows: composites to iron and carbon. Carbon is okay in the form of graphite, and the decomposition is controlled by the graphitizing agent at the cooling rate, and the dissociated carbon is in the form of graphite, which is very soft and without any strength. Thus, it reduces the hardness and increases the malleability of cast iron. And when the graphite is in a flake-like shape, like this, as in gray cast iron, the graphite breaks up the continuity of iron and greatly weakens it. But it also helps in absorbing vibrational energy, as a result of which green cast iron is normally used for the base of machine tools. The green cast iron. And gray cast iron is easily maintainable and is the cheapest form of cast iron because of its low melting temperature, higher fluidity, and negligible shrinkage on cooling. It is extensively used in casting processes. And this, the malleable cast iron. And it's the other form of cast iron is low as malleable iron, in which free carbon is present in the form of nodules in the matrix of cementite and ferrite. This is achieved by first chilling the casting so that all white cast iron is formed, followed by a controlled heat treatment process so that some of the cementite is transformed to ferrite and nodules of gray carbon. And this material is more ductile than gray cast iron. This foam is suitable only for complaints with very small section thicknesses, since all white cast iron is to form the starting point for malleable iron. And when graphite is present as small, round, and well-distributed particles, its weakening effect is small, and such cast iron would have higher ductility. This type of cast iron is called ductile or nodular iron, or spheroidal graphite, or simply SG iron. The form of graphite can be achieved by adding elemental magnesium or this of or cerium, or a combination of the two elements to molten cast iron. Magnesium is added in quantities of 0.06 to 0.1%, followed by the addition of ferrosilicon to promote graphitization. And during solidification, magnesium helps in distribution of graphite throughout the metal. And this is the round graphite. So for the cast iron, and for the green cast iron, the carbon is flake graphite. And for the malleable cast iron, the carbon is Modulus graphite. And for ductile cast iron, the carbon is in the shape of round graphite. But for white cast iron, the carbon is in the form of cementite. Okay. Ductile iron has better strength to weight ratio and better maintainability and higher impact value. Moreover, the ductile iron components are produced by cast process, wherein better control of component shape can be achieved compared to job forging. And thus, many components such as crankshaft and connecting rods manufactured usually by job forging are increasingly being replaced by ductile iron castings. Okay, and alloy steel is steel in which other alloying elements are added, such as titanium and nickel. And the stainless steel is formed when a certain amount of nickel and chromium are added. It includes astrological stainless steel and vertical stainless steel and magnetical stainless steel. Okay, let's do an exercise. Which one is made up of iron and carbon without any additional elements? Okay, which one have you chosen? Which one is made up of iron and carbon without any additional element? A. Ferrous metal. B. Non-ferrous metal. C. Carbon steel. D. Stainless steel. Who can tell me the answer?
Ferrous metals. A.
Teacher, maybe A.
Which one have you chosen?
A.
B.
A.
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 Yes.
A. Which one is made up of iron and carbon without any additional elements below non-ferrous metals? Okay, such as aluminum, titanium is non-ferrous steel. Okay, ferrous metal include cast steel and cast iron, and stainless steel is steel formed when a certain amount of liquor and chromium are added, so each had additional elements. So the answer is
B.
C. Carbon steel. Carbon steel is made up of iron and carbon. It's carbon steel. Okay, and ferrous metal includes carbon steel and alloy steel. Okay, and the answer is C. Okay, let's watch a video.
This bike is made of different ferrous metals.
Okay, can you hear the voice?
Yes.
Okay.
The muffler is low carbon steel. The chain is medium carbon steel. And the springs are high carbon steel. The brake disc is cast iron. The plastic hydraulic lines are protected by braided stainless steel.
Okay, so the answer?
This bike is made of different...
Okay, the answer, the muffler is low carbon steel, and the chain is medium carbon steel, and springs are high carbon steel. The brake disc is cast iron, and the plastic hydraulic lines are protected by braided stainless steel. Okay, let's take a break. Okay.
Yes. Wait. Why did I say?
Okay, let's beginning. Let's review the engineering materials.
We will introduce engineering materials usually used in manufacturing, and also we will discuss the material probabilities. There are three basic kinds of engineering materials usually used for manufacturing: metals, plastics, and ceramics. And also we have their composites. For metals, we can divide them into ferrous metal and non-ferrous metal. Steels, stainless steels, and cast iron belong to the ferrous metal. Aluminium, copper, titanium belong to the non-ferrous metal. For plastics, we have three kinds of plastics: thermoplastics like ABS and PVC, thermosets, and also elastomers like rubbers. Ceramics include the carbide, glasses, graphite, and diamond, and also some nanomaterials belong to ceramics category. When we mix different basic materials together, we can get the composites, like reinforced plastics. So here we have some product. This is real iron. This is aluminum can. This is the aluminum carbide. This is the titanium glasses. This is titanium used in the aeroplane engine. It's also titanium artificial teeth. It's copper. This is copper wire. This is stainless steel in our kitchen. It's also stainless steel. It's cast iron. This is also cast iron. Cast iron. Here we have ABS plastic and also high carbon steel. This is ABS plastic. Now this is PVC pipe. It's PVC box. It's PVC sheet. Okay, this is thermoset plastics. It's also thermoset plastic. This is rubber. Rubber band. Rubber duck. Glasses belongs to ceramics. It's also glasses. Diamond. It's graphite. This is the reinforced plastics. It's also reinforced plastics. Okay, back to real steel. You can see in our daily lives, different kinds of products are made of different kinds of materials. They are all engineering materials. So for different kinds of engineering materials, they have different properties. In manufacturing, we usually study the mechanical property, physical and chemical property of the material. So the material property is usually related to its internal structures. So before starting the mechanical properties, we need to know the internal structures, the crystal structures of different kinds of metals and also polymers. For mechanical properties, it includes strength, ductility, elasticity, hardness, fatigue, and creep. Physical and chemical properties include density, melting point, specific heat, thermal conductivity, electrical conductivity, and some other properties. Mechanical properties is important because we need to know the behavior of the material under some load in different kinds of manufacturing technologies. And for some specific kinds of manufacturing technology, the physical property and the chemical properties are also important. For example, in casting, we need to know the melting point of the specific kind of material. And some other technology like resistance welding, we need to know the resistance of the material. That belongs to the physical properties. In order to enhance the different kinds of properties of the product, we need to have some property modification processes like heat treatment and reinforcement. This is the outline of the metal alloys. First, we have pure metals, and then we add some alloying element into pure metals to form alloys. So for alloys, we usually use phase diagrams to study the microstructure of the alloys. And the alloy usually also called solid solutions. We have substitutional solid solutions and interstitial solid solutions. And alloys can be divided into ferrous alloy, like steel and cast iron, and also non-ferrous alloys, like stainless steel, copper alloy, aluminum alloys, and some other kind of alloys. After we make the alloys, we need to have some heat treatment to enhance the probability of the alloys. For example, quenching, annealing, tempering are usually used to enhance the mechanical property of steel. This is the outline of polymers. The polymers are plastics. It's made of mers. After polymerization, it becomes polymers. So for polymers, we usually study its internal structure. The internal structure of polymers can be divided into amorphous and crystalline. So due to the different level of cross-linking, the polymers can be divided into thermoplastics, thermosets, and elastomers.
Okay, now let's proceed to the next section, the mechanical properties of engineering materials. Okay, this is the physical properties, and this is the mechanical properties. The physical properties include density, melting point, thermal conductivity, electrical conductivity, error, color, frequency, volume, specific heat and temperature, and mechanical properties include strength, elasticity, stiffness, plasticity, ductility, roughness, toughness, hardness, roughness, and impact strength. Okay, there are some mechanical properties of metals. Modulus of elasticity, the initial slope of the curve related directly to the strength of the atomic bond. Okay, let me see the okay. And yield strength usually defined as the point at which a consistent and measurable amount of permanent strain remains in the specimen. And modulus and tensile stress, failure stress, ductility, and toughness. Okay. Now, the technical terms are in column A, and the means of them are in column B. Please match them. Let me see. For example, ductility is a measure of how much strain a material can take before rupturing. Okay, let me see. Okay. Okay.
妈妈，你在说什么呀？妈妈，你在说什么呀？
Okay, for plasticity. Okay, which one is it describes the plasticity? Which one? Plasticity means yes, the deformation of a material undergoing non-reversible change of shape in response to applied forces. This is the plastic. And for elastic, the property of a material that returns to its original shape after stress that made it deform or distort is removed. And for brighter, when subjected to stress, it breaks without significant deformation. And stiffness, which is describe the stiffness. The resistance of an elastic body to deformation. And durability, the ability to endure force without elastic deformation. And roughness, the quality to being unpleasant to the senses. Okay, and hardness, this is calculation by a sharp object. And okay, toughness, the ability of a material to absorb energy and plastically deform without fracturing. Okay, and this is the answer. Okay. Okay. For the tensile test, perhaps the most basic of all mechanical tests is the tensile test, which determines the stress of the material when subjected to a simple stressing operation. Typically, standard dimension test samples are cooled slowly and at uniform rate in a testing machine, while the strain, the elongation of the shape defined as the engineering strength, is the change in length over original length, and the stress, the applied force divided by the original cross-section area, and also the engineering stress can use this to describe the applied force over original area. This is the stress sigma, and this is the strain. Okay, this is the tensile test. Most common test for studying stress strain relationship in the test. F force pulls the material, elongating it and reducing its diameter. This is the typical test specimen, like this. And this is the tensile testing machine. The rigid test frame, and this is the grips. And the specimen is mounted between two grips. Then a uniform increasing tensile load is applied on the specimen. Okay, this is the force and the elongation diagram. And this is the beginning of the test. And this is the uniform elongation and reduction of cross-section error. Okay, sorry, wait a minute. Okay, and this state is the continued elongation, maximum load reached, and the lacking load begins to decrease and fracture. Then we measure the final length. Okay, and the final length over the initial length, we can calculate the strain. Sorry. Oh, sorry. My daughter is crying. Okay, this is the diagram, and from this point P, E, S, B, and K. The point B means the maximum stress of the of the metal, and K is the break stress, and P means the proportionality limit, and point E is elastic limit, means at this point the material stops behaving elastically and begins to behave plastically. When the stress is removed, the material does not return to its original length. S is the yield point. At this point, the material shows a large increase in strain for a small increase in stress. Let's see the curve. From O to P, the specimen extends in From O to P, the specimen extends in direct proportion to the load applied. And then, from after P, the material reaches its elastic limit, marked on the graph as point E. This point E. And up to the elastic E is the elastic limit. Up to the elastic limit, the steel will regain its original length when the load is removed. Okay, and after the elastic limit, the steel will not regain its original length. And this point S is the yield point. And from S to B, from S, there is a rapid increase in length for each increase in load. And up to B, there is load change in the cross section of the steel, and the maximum load is reached. And from B to K, after B, the specimen length further, but the load falls, and at point K, the specimen finally fractures. Okay. Let's see the elastic part. During the initial stress period, the elongation of the material responds to stress in a linear fashion. The rod reverts back to its original length upon relief of the load. And the elastic part, the slope in the elastic part of the stress strain diagram is defined to be the modulus of elasticity. E is sigma over epsilon. It's satisfied the Hooker's law. It reveals how stiff a material is and expresses the resistance of a material to elastic bending or elastic elongation. Yield stress separates the elastic region from the plastic range of material, and the plastic part, the permanent deformation, and tensile stress is the highest force that a material will sustain. Like in the point B, we call it sigma B, the tensile stress. And ductility, it is the measure of the amount of plastic deformation a material can undergo under tensile force without fracture. Okay, for hardness, hardness is the resistance of a material to penetration or skirting. Its amount for abrasion resistance as well as resistance to denting, and hardness is also directly related to strength. The harder a material, the stronger it is. Let's say a video.
Let's do a small experiment to understand the stress-strain curve. You see this thin steel wire? Let's see how its deformation happens. On the right, you can see the stress versus strain curve of the steel wire. Now, when the steel wire is under continuous tensile stress, as expected, it elongates. Now look at the graph. The elongation is linearly proportional to the applied stress. So this region in the graph is what it is. If the stress, that is the load, is released, what will happen? See there, the steel wire gets back to its original length. Now within this stress limit, the steel wire follows Hooke's law. What it means is the deformation is elastic. Now let's increase the load further. And what do we see? After a certain point, look at the graph. The wire is not following Hooke's law. That is, stress is no longer proportional to the strain. But if you release the stress, the wire still goes back to its original length. The limit of this behavior in stress-strain curve, that is this point, is known as the yield point. Now, if we increase the stress further, the strain will also increase, no doubt, but it will not follow Hooke's law. What it means is, even if there is a very small increase in stress, the deformation will be much more, and the wire will not return to its original length, even after we release the stress. So in this range, we can say that the deformation is plastic. And what happens? You increase the stress further? As expected, the wire will ultimately break, and that is the breaking point.
This video is about stress-strain diagrams.
In this video, we will provide an overview of engineering stress-strain diagrams for metals. Engineering stress-strain diagrams are developed from physical testing. A carefully prepared test specimen is subjected to a tensile test in a universal testing machine. The testing procedure is typically guided by a standard, such as ASTM, the American Society for Testing and Materials. This ensures that everyone who is performing the test follows the same procedure. Stress-strain diagrams allow us to plot the results from tensile tests and graphically identify important mechanical properties. As a reminder, stress is force per unit area that results from an applied load. Now, these applied loads could be in tension, compression, shear, torsion, or any combination. Strain is the physical deformation response of a material to stress. So an example of strain would be elongation of a material. When a test specimen is first placed in a tension testing machine, the force is increased and the strain is proportionally increased. If we look on our stress-strain diagram, this is the linear portion of our graph. If you were to release the specimen in this region, the specimen would return to its original shape, so no deformation has taken place. If we think about the specimen at the micro level, the bonds are stretching. This is considered the elastic region of the stress-strain diagram. The slope of the line in the elastic region is the modulus of elasticity, also known as the material stiffness. As we increase the load being applied to the test specimen, we will reach a point where there is no longer linear behavior. This is our proportional limit. With a little more loading past our proportional limit, we will have noticeable permanent deformation that takes place in our test specimen. This point is our yield stress. Yield stress is the stress associated with this point. Yield stress starts at 0.2% strain for most metals. What this means is, if we stop our tensile test and unload the specimen, we find the engineering strain is 0.002. Note, since there is a degree of elastic recovery, we do not draw the unload line straight down. We draw it parallel to the elastic curve. One thing to also realize is at a microscopic level, we have dislocation motion and permanent deformation that has occurred. That is why we are now in what we would call our plastic region. With additional force, the test specimen will eventually begin to neck. Or rather, the diameter or thickness of the specimen decreases in size. We call this point the ultimate tensile strength, or UTS. This is the maximum possible engineering stress that the specimen can take in tension. If we continue to load our specimen with additional force, we will find that the specimen will eventually fail. At this point, our bonds have completely broken. As we did with the yield stress, if we want to understand the engineering strain at fracture, we need to unload parallel to our modulus of elasticity line. For designers, modulus of elasticity, yield strength, and ultimate tensile strength are all important mechanical properties. We need to make sure we're designing components as well as products that can withstand the strength of the materials that are being used within the product. We need to make sure our components as well as our products do not go beyond the yield strength or ultimate tensile strength when they're in service, or failure will end up occurring. These are some of the elements that design engineers need to take into account from mechanical properties.
Okay, this is for the mechanical properties of metals. You should master the strength strain diagram and master some mechanical properties like the tensile stress, yield stress, and the elasticity and the plasticity, hardness of the material. Because for the machine design, we need to consider these properties of the metals. Okay. Now let's have a break. We will begin. We'll have a break for 20 minutes. Okay.
స్కూల్ పోతలేదంట రోడ్ల మీద డాన్స్ వేసుకుంటూ తిరుగుతున్నావంట మీ అమ్మ చెప్తుంది
Okay, let's continue. We will study this part, the heat treatment of metals. Below, heat treatment is thermal cycling involving one or more reheating and cooling operation after forging for the purpose of obtaining desired microstructures and mechanical properties in a forging. And the object of heat treatment methods is to impact certain designed physical properties to the metal or to eliminate undesirable structural conditions which may occur in the processing or fabrication of the material. And the commercial heat treatment in common use are annealing, normalizing, hardening, and tempering. They involve the heating of the material to certain predetermined temperature, sorting or holding at the temperature, and cooling at a prescribed rate in air, liquid, or retarding media. And the above treatment may be briefly defined as follows. Annealing. Annealing consists of heating steel slightly above its critical rate and cooling very slowly, usually cooled in air. And annealing relieves internal stress and strain caused by previous heat treatment, machining, or other cold working processes. And there are 3 different types of annealing processes used in industry. 1. For annealing. 2. Process annealing. 3. Oxidizing. And for annealing, it's used to produce maximum softness in steel, and malleability is improved. Internal stress are relieved. Process annealing is also called stress relieving. It is used for relieving internal stress that have occurred during cold working or machining processes. And oxidizing is used to produce a special kind of green structure that is relatively soft and malleable. This process is generally used to improve the malleability in high carbon steels and in wire drawing processes. Normalizing. Normalizing is a process used to relieve the internal stress due to hot working, cold working, and machining. The process consists of heating steel slightly above the upper critical rate, 30 to 50 degrees Celsius, and cooling to room temperature after holding for a while. And the more rapid cooling in air used in normalizing causes the oxides to decompose at low temperature, and this increases the dispersity of the ferrite cementite structure and the amount of perlite, or more exactly, causing eutectoid, and raises the strength and hardness of normalized medium, and high carbon steels by 10% to 50% as compared to alloy steel. And hardening. In any heat treatment operation, the rate of heating is important, and heat flows from the exterior to the interior of steel at the defined maximum rate. If steel is heated too fast, the outside of the part becomes hotter than the inner. A uniform structure is hard to obtain, and the hardness that can be obtained from the given treatment depends upon the following three factors: quenching rate, carbon content, and workpiece shape. Rapid quenching is needed to harden low carbon and medium clay carbon steel. Water is generally used as a quenching for this steel. For high carbon or alloy steel, oil is used. Its action is not as serves as that of water. When extreme cooling is desired, rain is used. Tempering. Hardening make high carbon steel and tool steel extremely hard and brittle and not suitable for most uses. By tempering or drying, internal stress developed by hardening process are relieved. Tempering increased the toughness of the hardness piece, and it also tends to make them more plastic or ductile. Okay. Let's say a last PPT. I'll find a last PPT. Okay, this is the rule of heat treatment. And this finger is 3 polycarbon steels from left to right. From left to right. And the carbon content will increase. Increasing the carbon content from 0.18% to 0.95% causes the amount of ferrite, the light error, 2 degrees, and the amount of perlite. Perlite is dark lamellar error, like this and this, to increase. Okay, so for iron and steel, the carbon is the most important alloying element in terms of its strengthening effect on iron. With the carbon content increase, the stress will increase, but the this will decrease. Okay, and this is the heat treatment process, and then purpose of any heat treatment process is to produce the desirable change in the structure of metal by heating to a specified temperature and then holding for time and then subsequent cooling. And heat treatment conditions are calculated by the following parameters: heat temperature, and time of holding, heat rate, and cooling rate. Okay. The transformation of perlite into oxalate can only take place at the equilibrium critical point, and very slow heating follows from the iron-carbon constitutional diagram. Under common conditions, the transformation is retarded and results in overheating. Okay. When overheated above the critical point, perlite transfer into oxalate, and the rate of transformation be dependent on the degree of overheating. And the time of transformation at various temperatures shows that the transformation takes place faster at a higher temperature and occurs at a higher temperature on a quicker heating. Okay. For instance, on quick heating and holding at 780 degrees Celsius, the perlite to oxalate transformation is completed in 2 minutes, and on holding at 714 degrees Celsius in 8 minutes. Okay, this is the transformation from perlite to oxalate. Okay. And in place earlier occupied by lamellar of perlitical cementite, the content of carbon is greater than in places of ferritic lamellar, and this is why the oxalate just formed is inhomogeneous. Okay. Let me say, at the beginning of perlite to oxalate transformation, the first grains of oxalate form at the boundaries between the ferrite and cementite, and the two structural constituents of perlite. Since these boundaries are very developed, the transformation starts from formation of a multitude of fine grains, and therefore, at the end of the transformation, the oxalate will be composed of a great multitude of fine grains whose size characterize what is called the original oxalate grain size. Okay, and the size of plastic grains at same temperature of the oxalate to perlite transformation depends on that of the oxalate grain from which they have formed. And the oxalate to perlite transformation is essentially the decomposition of oxalate into almost pure ferrite and cementite. And we can say the transformation from oxalate to perlite can only start at a certain undercooling when the free energy of the ferrite carbide mixture is lower than that of oxalate. And the lower the transformation temperature, the higher the degree of undercooling and the greater the difference in free energies, and the transformation proceeds at a higher rate. Okay, and we'll see that this is the transformation, and the initial stage is characterized by a very low rate of transformation, and this is what is called incubation period. And the rate of transformation increases with progress in the transformation. Its maximum approximately corresponds to the amount when roughly 50% of oxalate has transformed into perlite, and the rate of transformation then diminishes and finally stops. The TTT diagram, the horizontal line below the curves in the diagram determines the temperature of the diffusion is martensite transformation. The martensite transformation occurs by a different mechanism and will be discussed later. Okay. Diagrams of the type we discussed are usually called TTT diagram, time temperature transformation, or C curve, owing to the specific shape of the curves, the structure and the properties of the products of oxalate decomposition depends on the temperature at which the transformation has taken place. Okay, this is the TTT curve or C curve. For this cooling rate, we can obtain colors perlite. Increase the cooling rate, we can obtain fine perlite. Okay, if we cool in air, we can obtain the fine perlite. And this is for quenching the metal, we can obtain martensite. Okay, and at high temperature, low degrees of undercooling of coarse-grained mixture of ferrite and cementite is formed, which is easily distinguished in the microscope. This structure is called perlite. This lamellar perlite is a mixture of ferrite and cementite. Okay, and at lower temperature and with greater degrees of undercooling, more dispersed and harder. And the lamellar structure of the ferrite and cementite mixture is only distinguishable in electron microscope. This structure is called Eutectoid. Okay. Thus, perlite, sorbite, and Eutectoid are the structures of the same nature. Ferrite and cementite, the mixture of ferrite and cementite, but a different dispersity of ferrite and cementite. Okay, and this is some mechanical properties of the perlite. Okay, and the perlite structure may be of two types: granular and lamellar. Granular is in which cementite is present in the form of grains, and for lamellar, the cementite is present in the form of platelets. Okay, homogeneous oxalate always transforms into lamellar perlite. Therefore, heating to a high temperature set up favorable conditions for the formation of a more homogeneous structure and thus promotes the appearance of laminar structure. Okay, this is for the inhomogeneous oxide. Produce granular perlite, okay, at all degrees of undercooling. So heating to a low temperature results in the formation of granular perlite on cooling. But this is the microstructure of upper perlite. It's very coarse and low stress and ductility. And this is upper perlite, and this is the lower perlite. It's a fine perlite. It has higher strength and hardness. Okay. The types of heat treatment annealing. Okay, that's the types of annealing. Okay, and this is all the types of annealing and tempering. Okay, and today we review some key points of engineering material and its and their mechanical properties and the heat treatment. Let's review it again. The materials, the classification of materials. We focus on the porous materials, metals, porous metals, and it include irons, carbon steel, steel, stainless steel, and so on. And this is the iron carbon phase diagram. It can know that the fellows can be classified as steel and cast iron. When carbon content is more than 2.11%, we call this cast iron. And when the carbon content is less than 2.11%, it's carbon steel. Okay, and the carbon steel include low carbon steel, medium carbon steel, high carbon steel in terms of the carbon content. For low carbon steel, the carbon content is less than 0.3%. And for medium carbon steel, the carbon content is from 0.3% to 0.6%. And for high carbon steel, the carbon content is from 0.6% to 1.7%. Okay, we also can classify the steel as Eutectoid steel, hyper-Eutectoid steel, and hyper-Eutectoid steel. Okay, this is the phases in steel. Ferrite. Ferrite is very soft and ductile, and it has a body-centered cubic, but the okay, but the solubility of carbon in ferrite is very, very low, and this is the microstructure of the ferrite. And this oxide, and it's soft and ductile, and it's a FCC structure. FCC structure. And that iron is occurs at a high temperature. And cementite is a mixture of ferrite and perlite. Okay. For the steel, the microstructure at room temperature. Note that for Eutectoid steel, the composition is with 0.8% carbon. The structure at room temperature is polite. And for hyper-eutectoid steel, the microstructure at room temperature is perlite and ferrite. And for the hyper-eutectoid steel, with the carbon content larger than 0.8%, the microstructure at room temperature is perlite and cementite. At this temperature, there is a eutectoid reaction. The oxide transfer to ferrite and cementite, and this is the eutectic reaction. Okay, the liquid transfer to oxide and cementite, and this is for the cast iron. This is for the steel. Okay. We have no this, and then for cast iron, note that the form of cast of carbon, it depends on the form of the carbon. If the carbon is in the form of a flake graphite, is we call that green cast iron. This is the carbon, or the graphite. It's flakes. And for malleable cast iron, the carbon is Modulus graphite. And for ductile cast iron, the carbon is round, small, and well-distributed particles is a graphite too. And for white cast iron, the carbon is in form of cementite. Okay. This is the classifications of steel and cast iron. The steel can classified as carbon steel and alloy steel. For carbon steel, it has the element of iron and carbon only. For alloy steel, it can add some alloying elements like titanium, nickel, chromium, and so on. And this is for the cast iron. The classification like this, it includes green cast iron, white cast iron, malleable cast iron, and ductile cast iron. Okay. This is for the classification of ferrous metal. And this is for the mechanical properties of metals. In this course, we focus on the mechanical properties like strength, elasticity, plasticity, ductility, hardness, and impact strength. Okay, like this. And this is for the tensile test. Tensile test. From the tensile test, we can obtain some important mechanical properties. Okay, like the yield stress, the tensile stress, break stress, and we also can know the plastic. We can calculate the strain. Okay, and this is the residues of the tensile from O2P special. The specimen extends in direct proportion to the load applied. And so after P, the material reaches its elastic limit. And up to the elastic limit, the steel will regain its original length when the load is removed. And after the elastic limit point, after point E, the steel will not regain its original length, and then it reaches the point S. S is the yield point. From S, there is a rapid increase in length for each increase in load. So it's a plastic deformation. And up to B, there is no change in the cross-section of the steel. The maximum load is reached. And then from B to K, at B, the specimen length further, but the load falls, and at point K, the specimen finally fracture. Okay, and this is for the elastic part. The elastic part from the point P, the proportional limit. It satisfies the Hooker's law, means that the modulus of elasticity E is equals to sigma over epsilon. Okay, and the yield stress. The yield stress from the yield stress means this point S. S is the yield point, and the corresponding stress is the yield stress. Okay, the yield stress separates the elastic region from the plastic region of the materials. And then the plastic part, plastic deformation is permanent deformation. And then tensile stress, the highest force that a material can sustain. And ductility is also important, and hardness. Okay, and then we review the heat treatment of steel. It includes annealing, normalizing, hardening, and tempering. Okay, now we will do some exercise. Okay, look that your grade for this course is depend on your daily performance and the final test, and the exercise will be graded as part of the finals of our course, and the exercise account for more than 1/4 of the course grade. Okay. Let me see. I will share. You know where it's practice the exercise. Okay. Can you see the Word document? Okay. Can you see? Can you see this?
Yes, 老师。
Okay. Okay. Do the
Can't see the word properly, 老师.
Okay. You do this exercise now and submit your answer to me. Okay.
老师 in the comment section. No.
You see all of the exercises.
老师 how should we submit it?
How to submit? Let me see. Okay, submit. Maybe. Okay. And there to submit your answer. Okay.
老师 how?
From this there. Submit. Use this. Okay.
Not like that. No.
Last, please, can you give the PDF to our group and this question so we can solve the question and send it to the group? Hello, Laushi.
Hi.
Laushi, can you please send the PDF and this question to our group?
Oh, send it to group. Okay. Okay. I send
Yes,
it to
yes,
the group.
yes. Yes.
I send it
Then
to
it
the
will
group.
be easy to answer it.
Okay. Group. Let me find the group. Where is the group? Let me. Okay. Wait a minute. Let me find it. What to find? Can you see? Can you find the practice in group? Can you find?
Yes.
Yes, Laushi, yes.
Okay. Do the practice now. Okay.
Okay.
Okay. So also send the question paper.
Sorry.
Laushi, the PDF. Can you please send the PDF of this class?
PDF. You mean the PPT?
Yeah. Yes, yes,
PPT.
PPT.
Oh, PPT. Okay.
Yes,
I'll
yes.
submit the PPT. Okay. Wait a minute.
Okay.
Mm.
Lao Shi, can you please tell the time when we have to submit the answers? Hello, Lao Shi.
Aushi,
Uh,
when is the
oh,
last time to submit the answer?
uh,
Could you please tell me?
you have 20 minutes to do the exercise, and then send the answer to my email address. Okay, and then after After yeah, you need to send the answer to my email address.
Right now.
Email address, my QQ 3445 3447552 at qq.com. My email address. Do you have my email address? Let me see my email address.
Yes, Laushi, you already sent it to our group.
Yes, Laushi, we have.
No, let me see my email address. Okay, find it.
Laoshi, we have to send it right now.
Okay, you can see it right now. This is my email address. Okay, let me see. No. This is my email address. This is my email address. Okay.
Okay, Laoshi.
Okay, you send the answer, and 20
Laushi,
minutes
we
later.
need some time to do the homework.
What?
Urabyutse urarushye
Okay, class. Have you finished the exercise? Have you finished?
Can you confirm the ones you've gotten?
Okay, finish. Let's explain the answer. So, ferrite is which structure and authorite is which structure? Then we choose ferrite is BCC structure and the authorite is FCC structure. So the answer is B, A. Okay, and then the carbon content of medium carbon steel is
0.8,
yes, we choose B, 0.3 to 0.6%. Okay, and this is for low carbon steel, and this is for the high carbon steel, and this is for the eutectoid steel. Okay, so the answer is B. Okay, answer is B. And for this question, at which point the material stops behaving elastically and begins to have plastically? So the answer is B, elastic point. Okay, elastic point. And for this question, the strength of low carbon steel is lower or higher than that of high carbon steel. We choose lower. A. Yes, the strength is increased with the carbon content increase. So strength of low carbon steel is lower than that of high carbon steel. So the answer is A. And this, the plasticity of low carbon steel is lower or higher than that of high carbon steel. You choose which one, A or B? A or B?
It's lower.
Plasticity.
Higher, yeah.
Plasticity.
Okay.
Plasticity will increase with the carbon content decrease. So we choose B, higher. Okay. The plasticity of low carbon steel is higher than that of high carbon steel. The answer is B. Okay. Answer is B. And this question, the hardness of low carbon steel is lower or higher than that of high carbon steel?
Lower.
You choose
Lower,
which?
yes.
Hardness. Yes, the answer is A. Okay. Answer is A. Hardness of low carbon steel is lower than that of carbon steel because when the carbon content increase, the hardness will increase. Okay. And the microstructure of eutectoid steel is Eutectoid steel is the steel with the composition contain 0.8% carbon. So the answer is A, perlite. Okay. Yes, eutectoid steel, the microstructure is perlite. And perlite and ferrite is for the hypo-eutectoid steel, and this is for hyper-eutectoid steel. Okay, so the answer is A. And the microstructure of hypo-eutectoid steel is B, perlite and ferrite. Okay, and after annealing, the microstructure of carbon steel is after annealing. After annealing, we can obtain the microstructure of perlite. Okay. We choose A, perlite for annealing. annealing can obtain the microstructure of pearlite. Okay. Okay, A. And after quenching the microstructure of carbon steel is, after quenching, we can obtain the microstructure of martensite. So answer is D. Okay, D. And the hardness of a leaning high carbon steel is lower or higher than that of quenching high carbon steel. You choose A or B. A or B. Answer B. B. Okay, let me say the microstructure of a leaning high carbon steel is pearlite. Okay. And the microstructure of quenching high carbon steel is martensite. So this means the hardness of pearlite is lower or higher than that of martensite. So you choose A.
Lower.
A, lower. Because the martensite, the hardness of martensite is very high. Okay. The hardness of martensite is very high, and quenching high carbon steel, we can obtain martensite. Okay. So answer is A. Okay. And that's all for today. And next time, next class, we will learn Unit 2. Unit 2, the strengths of meshing elements. Okay. And let's stop now. See you next time.
Okay, bye-bye.
Loshi. Hello.
What?
Yeah, Loshi, can you share the PPT of next class before the class?
Okay. I send it to the group. Okay.
Okay. Thank you.
Okay. Okay. Bye bye.
Bye-bye, Loshi.
Bye bye.
What is live action?